So welcome to this second short video on third law of thermodynamics. So here we will just justify the statement why it is impossible to decrease the temperature of any system to 0 Kelvin in a finite number of steps. So how do we rationalize this statement? So let us start with this. du is equal to TdS minus PdV, and we know that du is equal to Cv dt for 1 mole of ideal gas. Okay, so your Cv dt will be equal to TdS minus RT dV by V. Now if I divide both the sides by temperature, so it will be Cv dt by T is equal to ds minus R dV by V. So what will your ds be? ds is equal to Cv dt by T plus R dV by V. Now if you know a little bit of this, so dx by x is given by d ln x. Okay, therefore dt by t you can write it as Cv d ln t plus R d ln V. Now for a spontaneous adiabatic process, which takes the system from T1 to a lower temperature T2. Note that T2 is your lower temperature. Okay, so what is your delta S is given by Cv integration d ln T from T1 to a lower temperature T2 final temperature plus dV by V from its corresponding volume to V2 should be greater than or equal to 0, right? Entropy of spontaneous adiabatic process should be greater than or equal to 0. So this will give you Cv ln T2 by T1 plus R ln now this is same as minus Cv ln T1 by T2 so now if T2 is equal to 0, your this value will correspond to minus infinity. Okay, now to compensate that delta S should be greater than or equal to 0, this value should become plus infinity, which is impossible. So there is no actual process that can take you to 0 Kelvin. Okay, so but in fact you can get very close. You can get very close in Professor W. Ketterle's experiments on Bose-Einstein condensates. Okay, so atoms are cooled to nanokelvin. So which means this is the lowest temperature that is achieved. So about 10 to the power of 9 Kelvin. So this is your okay, but not to 0 Kelvin. Okay, in fact this guy got a Nobel Prize for this. Okay, he's from MIT. So that was your second video. See you all. Bye.